Elasticity has got to do with the ability of a material when stretched, especially when it is not beyond its limit, then you leave it, it gets back to its normal position. It reforms. And so if a rock sample, for example, you have a couple of load sitting on top of a rock, it will be going through some kind of stress on it. Because the load is sitting on, some compression will go on or will happen within it. And once this compression is happening, as soon as you relieve it from that load that was being exerted on it, it goes back to its original state. When that happens to a rock, that phenomenon of the material being stretched and resolving itself to its original position is what we term as our elasticity, or that behavior of elasticity. So we are saying elasticity of a rock is the ability to change form or volume under the effect of any external force and return to its original position. So when we have this situation, we say, so this can only happen if the load you are exerting onto the material does not exceed its limit. Because remember, we did uniaxial compressive strength, and we said that it is the amount of load the rock can bear before failure, the strength. So in the same way, whilst we are subjecting you to these external forces to change in volume or in length, we must be sure that we are not, you will still be within your strength zone in order to return to your original form. Otherwise, if you exceed the strength, the material's threshold, then it is no longer going to be in its original state. It's just like these rubber bands that our women have been using to tie their hair. You realize that, or even if you've been using these rubber bands to tie items for a long time, at some point it changes in terms of volume. The space increases, the area within it increases, such that it doesn't go back to its original form when you bought it or when you had it. And then at some point, it gets to a state where it looks like it has already failed. It becomes too soft. And when we have that type of state, we say that a particular material is more or less in its elastic state. So we say that it is called the permanent set, okay? Permanent set or elastic state, where the material gets to a form such that it cannot return. It has not failed completely, but it is no longer as it used to be. It is deformed in some kind of way. And so we have to always be sure that when we are exerting materials to this type of test, we don't exceed the threshold of the material. Then we can have it returning to its original state. So now, in applying elastic principle, remember in our earlier slides, we stated that our rock had certain behaviors and we gave an acronym for it. So let's see. We are saying that isotropic simply means when we test the rock sample, the strength properties of the rock sample, irrespective of the direction, we will get the same strength values or strength properties because the samples or the particles and minerals are uniformly mixed. Irrespective of the direction or where I pick a sample to test the strength, I should get the same value. Then linearly elastic, again, because all other properties are the same. When I subject the sample to a load, it reacts proportionally in terms of deformation. So when I increase the amount of force, it will deform according to the quantity of force I am exerting on it. And that will give us some kind of a linear elastic behavior when you plot this force the stress against the strain, you will get a linear line. And that is what we have here as. And this Chile is the normal construction material, which is used by the mechanical engineering department. All their properties they determine, or the stresses we determine within these mechanical fields. For example, strength of material and basic mechanics. The assumption is that the rock or the samples they are dealing with have this property. But you know that our rock sample is a natural material whose properties you cannot define. They are not homogeneously mixed. It is not continuous. They are anisotropic. And so it is hard to apply some of these mechanical principles like elasticity and strain. But then when we get to trying to apply the principle of elasticity, it was built for normal construction material. But as rock mechanics engineers, we have not proposed any special theory of elasticity for the rock. And so if we want to determine the elasticity of the rock, we have to go and pick that principle from the mechanical department and now assume that our rock is similar to any construction material. Then we can use their principle. And that is what this slide is talking about. That in applying the elastic principle, the following assumptions are made. The rock is assumed to be continuous, homogeneous, linear, and then elastic as well as isotropic. So we are now assuming that if our rock material were to be any other construction material whose properties are determinable, you can determine the properties such that they don't vary with time, just like they behave, which is the normal behavior for our rock, then we can use that principle. So we are only making that assumption to determine the elastic properties of the rock. Otherwise, we cannot. Take, for example, you want to determine a rock's strain. And I said the last time that strain is the deformation that occurs when you apply a stress to a rock sample. So for example, when you enter any other class for a lecture or a model, you are subjected to some amount of stress. If it is operations research, you are subjected to some stress. And those stresses, you will go back to your original state after you have finished the test or the model examination. Then you go back to your normal form. Then you prepare yourself for another. Once you go in there and you are broken down, you can't come to my class. You see how it is? And so in the same way, we are looking at our rock sample such that it has all of these properties so that when we are applying the principle is saying that when I subject the rock to any stress, it should go back to its original form. But you are saying your rock is discontinuous, it is inhomogeneous. How will it go back to its original form? It won't work. And that is why we want to make this assumption that the rock is no longer D-I-A-N, Dian. Rather, it is Chile. Then we can use this principle. So now that we are all on the same page to use that principle, then we can apply any theory of elasticity to it. And then to determine that, that is how come when we are subjecting our rock sample to the uniaxial and the triaxial test, there's always some cables that we attach to the sample to measure the deformation. Why do we do that? We do that because our rock is such that when it deforms, it usually crashes. And so once you take the machine off it, you are left with pieces of the deformed rock. How do you put it back to measure the deformation that occurred earlier? You can't do that. And so we place those gauges there so that as the load is being applied, the machine will also be automatically be measuring the deformation, which is the strain. And then the moment it fails, the force is stopped. It's no longer applied. And this guy will also stop recording the strain. So we get the two values simultaneously. So then let's see. So deformation or strain of a loaded rock material is small and may be neglected in certain equilibrium conditions. So we are saying that sometimes these deformations that occur may be too small, such that you don't even need it. Then we have Hooke's law. States that deformation of a body is proportional to the force, the action force, which can be expressed in an equation we shall see. So let's take, for example, the amount of force. So for example, if I pick this thing and I was to place somebody's finger on a table, if I raise it by 10 meters high and I leave it, the deformation will vary from someone who will raise it at 20 meters high and leave it to settle on your finger. In the same way, if you have a phone and you raise it, you are at a certain height and it falls off, the deformation will vary from, if let's say you are even on the where the MSC, mining MSC is, okay, CB2, then first floor, you leave a phone to fall or a laptop to fall. The deformation will vary from if you are on the second floor or the third floor. That is just what this principle is trying to tell us, that your deformation, the quantity or the amount of deformation is always varying respect to the amount of force that will be exerted. And the deformation here is talking about what? The stress, the strain. And then the force is what we term as what? The stress. So let's see this. So the change in length here is talking about if I exert compressive strength here, what do you think will be happening to this sample? It will reduce in terms of height, but then it will elongate along the axis. And that elongation along longitudinally this way is what we term as the strain. So we have this formula, which is more or less expressing that of the modulus or the Hooke's law. And then this E here is what we term as the modulus of elasticity. So usually we mention modulus of elasticity, Poisson ratio, and whatnot. Then the Poisson ratio is trying to look at how difficult it is to squeeze the rock in all directions. Or let's use this, a rubber ball that these kids play with. When you begin to compress it, it will try to escape through other places within your finger. Any other hole that is around or available for it, it will want to escape through it. So we want to measure how difficult it is to squeeze a given rock sample. And so if it is very difficult to squeeze the rock sample, then we are measuring higher values of what? Poisson ratio. And so it is a very good property of the rock we need to know. So it's just like when I'm compressing, I am supposed to measure some strain values here. Then again, when I'm compressing on the side, I'm supposed to measure some values here. How difficult it is for me to even compress this rock and put all of it together, assuming I was to put this entire rock into a smaller shape so that I can hold in my hand, then that property of the rock I'm trying to determine is what we term as the Poisson ratio. If it is difficult to squeeze the rock, then it means if you create a structure and you place, and assuming the structure is this, and you are placing a rock sample is sitting on it and on the sides, it will be very difficult for you to just squeeze or destroy that particular rock sample by way of the load you are applying to it. So it is some kind of a resistive force of the rock, a property of the rock to prevent failure. And so again, with Poisson ratios, we are looking at other higher values. But mostly, theoretically, we say the Poisson ratio of the rock varies from 0.1 to about 0.5. And it is unitless because you are using the longitudinal, okay? You are trying to use that of the lateral against the radial. And so it's a ratio of the squeezing when you compress the sample axially and that of radially. And so that ratio becomes unitless.